So, I'm going to talk tonight about strong field molecular dynamics. And what I mean by that is the motion of the nuclei when you expose a molecule to strong fields. Okay? Now, I'm going to get much more specific than that in a minute. But again, I want to remind you, this is a lecture, not a talk. So do like you guys did the other day, ask lots of questions. Okay, if I only get through half this talk like the other day, that's great. We had lots of discussion, so let's do that again. I know you're all trying to recover from dinner, but let's make an effort. This is work done by, I'm going to show work done by former students and postdocs. So thought I would start with a goal statement. You know, more or less the theme of my own group's work, and that is that we want to try to find a first principles theoretical treatment, either or both computationally and analytically, of strong field dynamics of atoms and molecules. Okay? I told you about one such treatment the other day. What I'm going to talk about today is going to be more on the computational side. Okay? I'm not going to tell you about the computation itself unless you want to hear the details, but you'll have to ask for that. Okay? Rather than I'm going to focus on some of the basic stuff and some of the results, some of the physics. Okay? But because we want to do first principles treatments, we're pretty limited actually on what systems we can actually treat. Okay? And so that naturally leads us to consider benchmark systems like H2+. If you want the simplest molecule, that's H2+. Okay? This particular system has the advantage that it can also be measured in its completeness by a colleague of mine at K-State, Itzhak group. Again, several of the representatives are here. There's one other group in Germany that can make measurements on such systems as well. But being able to make direct measurements on these, starting from the ion, not starting from the neutral, is a big advantage, especially when we want to compare theory and experiment. Okay? So by removing uncertainties in the theory, by treating these benchmark systems, we can focus on the physics and not worry about whether our approximations are leading to the physics that we see. And it can help us sort out experimental issues, wherever they might be. And this has come up in this collaboration between my theory group and Itzhak's experimental group. Okay? It was actually consideration of this system that led us to that sort of general approach for CE phase effects and multicolor control that I told you about the other day. We did the calculations first for CE phase effects in this system, and then we wanted to try to understand it. Okay? That's how we got to that approach that I described last time. Okay? So having a simple system where we can actually do complete calculations is a big benefit to test those kinds of ideas and to lead you to the notion that you should have a chance of understanding them in a simple way like that. Okay? Moreover, when you have such a system, we can test approximations that folks are using in the field. And there's a number of those. One of those is the axial recoil approximation. Now, how many in here have heard of the axial recoil approximation? Small handful. Okay, good. So I can explain that. I'll do that in a couple slides when we get to that. Okay? But that's just, it's a common approximation used in this field. And one of the reasons is, and I don't know that this has been explained in so much detail, but experimentalists in the field can do quite exquisite, detailed measurements these days. Okay? You've heard the terms. You've heard VMI, for instance. You've heard Coltrims. What that means is that for a system that breaks into, say, 2 or 3 pieces typically, they can measure all of those pieces, all those fragments, and do it in coincidence, not with VMI, but do it in coincidence such that they know all those fragments came from the same molecule or atom, as it may be. Okay? And then using kinematics, what they know about their spectrometer, they can actually get the momentum of all of those fragments. Okay? Now, if you have 3 fragments, that's already 3 momentum vectors, or 2 relative momentum vectors. That's 6 dimensions of data that you have to deal with. That's already quite a lot of information. Okay? Some of it can be state resolved to some extent. Okay? But in particular, what they can measure is the directional distribution of the final product. Okay? So the momentum imaging technique that ITAMP group uses is very similar to, say, Coltrane's. Okay? So what momentum distribution do they measure, though? Do they measure, if they get, say, some momentum distribution, you've seen a few, does that tell you which direction the molecule broke? What do you think? Just think about it a minute. When you measure the fragments and get the relative momentum distribution of those fragments, does that tell you, if they were, say, the nuclei, does that tell you the direction that the molecule was aligned, for instance, when it broke? So you measure a particle out here. Let's just do hydrogen. Proton and hydrogen, you measure that. Does that mean that the molecule was like that when it broke and it just went like that? Well, what you've in fact measured is only the final momentum, the asymptotic momentum. The momentum as t goes to infinity. Because guaranteed, wherever your detector is, that's t equals infinity on the scale of these reactions. Okay? So what you measured is t equals infinity. You don't in fact know where the molecule was when it broke. Okay? That's actually what the axial recoil approximation is saying. That if you measure it here, you assume that the pieces just went in a straight line to that point. So that that momentum distribution you measure out here is in fact what it was when it broke. That's the approximation. And that's one of the things we can test when we solve a system like this and can solve it accurately and exactly, nearly exactly. Okay? But in a more general sense, molecules in intense fields are non-perturbative systems. Lars told you a little bit about this. You've heard some other folks talk about molecules. So we have to come up with non-perturbative techniques. Those are notoriously challenging. And again, I'll tell you a little bit more about those. Lars also mentioned that when you have molecules, and when you shine a light on the molecule, where do you think that energy is mostly going, at least initially? The electrons seem like they're easier to move around, right? Seems like it's easier to deposit energy into those electrons somehow. Okay? But that energy has to go somewhere, especially if you want to dissociate, if you want to initiate chemical reactions, if you want to make the nuclei move, then you have to have this correlation between the electrons and the nuclei that Lars was talking about. You have to have exchange of energy between the electronic and nuclear degrees of freedom. Okay? And if you can understand that, hopefully you can control it. And by the way, in the field, that sort of goes without saying, that our whole goal ultimately is we want to make all this engineering. Right? We don't want this to be physics forever. We want it to move to engineering. We want the engineers to be able to, the quantum engineers, to do what they want with the system. We're the ones figuring out all of the principles of that to lay it out for them so that later on they can just do like engineers do and follow rules of thumb and make it work, right? Okay? But the ultimate goal of all this is understanding it well enough to control it. Okay? Now the nuclear motion is going to be slow enough in a lot of these reactions in strong fields, on the order of, say, a few eV, to be quantum mechanical. Okay? And the measurements are going to be such that the quantum mechanics is important. With these imaging techniques that these folks have, they can measure the vibrational states, individual vibrational states. They can have vibrational resolution in the spectrum. That means that you have to have vibrational states in your representation, which means classical mechanics for the nuclei has to, at the very least, be augmented to get that kind of structure. Okay? Because, of course, in classical mechanics, you don't have discrete energy levels. However, it's not slow enough to become simple. It's kind of in a difficult region. Okay? And again, all of this effort is to lead to making molecular movies. Linda talked about that, and several other folks have talked about that. Okay? So the goal is to image it, understand it, eventually control it, direct it where we want. In the particular case of H2+, it is the simplest molecule. You might ask, hasn't it been done already? And the answer is actually no. Even the simplest one hasn't been done in its entirety. Okay? And if you think about it, H2+ is 2 protons and 1 electron. That's 3 bodies. That means you have 6 degrees of freedom once you go to the center of mass frame. Okay? If you want to be technical and you have linear polarization, you have 5 degrees of freedom. But you're still trying to solve a 5-dimensional partial differential equation, the Schrodinger equation, and propagate it in time. Okay? That's still quite a challenge. Only recently, relatively recently, have folks been doing that for helium, which is a simpler system. And even then, it's mostly not for the strong field 800 nanometer small photons. They're still on the bigger side. Okay? So even that problem, which is the same dimensionality, but simpler technically, is still evolving in the street. And one of the problems is that the fact that you have these 2 centers, these 2 protons, we call that the 2-center problem, makes representing the electronic part difficult. Okay? Makes representing everything at once a challenge. Because if you have helium, if you have an atom, you have a nice center of force. You can use spherical harmonics, right? That seems like a nice basis. You can use angular momentum kinds of bases. When you have 2 centers, you don't have that option and things become more complicated. Okay? Don't even talk about 3 centers or 4 or doing a polyatomic. That becomes really very, very difficult. Okay? And by the way, that means that, for the most part, I haven't actually said anything specific to H2 plus yet. The 6D, of course, is for H2 plus, but any diatomic molecule has more or less these same properties. For instance, more or less 3 physical processes, 3 classes of processes are important. You can have ionization, which is, of course, electronic motion. You can have vibration, which would be, the radial motion, or rotation of the whole system, the nuclear rotation. Okay? And, of course, Lars already mentioned the scaling, how these relate to each other. If you set the electronic time scale to be unity, then vibration scales like square root of the reduced mass. Okay? And H2 plus, that's a factor of, what's the reduced mass for H2 plus? In atomic units, if you like. 2, what? What's the mass of a proton in atomic units?
1800.
1800. So what's the reduced mass of H2 plus? Of the 2 protons? 900, right? 1,000. Call it 1,000. Okay? So, actually 900 is convenient. What's square root of 900?
30.
30. So there's a factor of 30 at the minimum, because this is H2 plus. That's the lightest one. So at a minimum, there's a factor of 30 in time scales between the electronic motion and the nuclear vibration. There's another factor of 30 to the rotational time scale. Now, if you like, you can replace energy scale, frequency scale, whatever quantity you want to compare. The nuclei are heavier, slower, and of course that's what leads to the Born-Oppenheimer approximation. Okay. Now, let me ask that question. How many of you have seen the Born-Oppenheimer approximation? So, okay, maybe I should ask the other way. How many have not seen it? Okay, so that's not so many. So I'll go through the next one a little bit quicker, since most of you have seen it. You may not have seen it quite in as much detail maybe as I'll show you. I had to throw some equations at you. I'm a theorist after all. So, we'll get there in a minute though. So some of the things that I want to test, that we'll talk about in terms of the physics, as I said, the axial recoil approximation, which assumes that the fragment distribution that you measure at infinity in time, infinity in distance, is the same as it was when the bonds broke. Okay? And you'll often hear people not even state that they're using the axial recoil approximation, just say, look, we measured this distribution, that's the way they broke. Okay? So you have to understand that, approximations like this lie behind and just are sort of a fundamental assumption that are made in many talks and many papers, things like that. Okay? When do we expect it to work? Well, one of the assumptions that leads to the idea of the axial recoil approximation is that the radiokinetic energy is large compared to any angular energy, okay? To rotational kinetic energy. If that's true, then they're going to fly apart before they have time to rotate. That's the idea, okay? By the way, the axial recoil approximation was introduced in electron scattering, photoionization, that sort of thing, where you had really big photons. So you gave things you gave the ionized electron lots of kinetic energy, okay? Or the nuclei, you gave them lots of kinetic energy, okay? That may not be true in strong field processes. This axial recoil approximation, as I mentioned, is invoked in coincidence measurements to talk about extracting molecular frame observables, okay? Because that's the other point, is that when you're doing calculations for molecules, you typically, and when I say calculations, things like, say, a photoelectron distribution, you typically do those in the frame where the nuclei are fixed. You go to the body frame, okay? The electronic coordinates are pinned to the nuclei and move with that, okay? But of course, if you do a measurement of the electrons in the lab, your molecule is not fixed, it's moving around, okay? And so comparing that to what people typically calculate, just because that's the easier thing to do, either you have to average the calculation over all those angles, or you have to take away that rotation in the experiment. And so one way people do it is they say, well, we've measured the momentum of these fragments, so we know where they are, so we can go to that frame. We know the transformation of the frame where those things are fixed, and call that the molecular frame. That, again, is a little bit tricky because you've only measured where they were, or their momentum, at the final time. So it is a molecular frame, but it may not be the one that you think it is. Okay. Another common approximation, common concept that you'll hear mentioned is geometric alignment. Okay. Maybe not in so many words again. And the idea is that the molecule doesn't have time to rotate during the pulse, okay? Which means that those molecules are already aligned to the pulse, because normally you start with an isotropic distribution of molecules. So if you have a linearly polarized laser, only those whose transition dipole is aligned with that will dissociate, they'll preferentially dissociate. And again, the argument is, as I said, molecular rotation is really slow. Sorry, that's the laser polarization. Molecular rotation is really slow. So it doesn't have time during, say, a 10, 20, 30 femtosecond pulse to actually rotate during the pulse, okay? Because a typical rotation time scale is hundreds of femtoseconds to picoseconds, okay? And so it sounds quite plausible that a 10 femtosecond pulse is short enough that there's no rotation. That geometric alignment sounds like it makes sense. So that's one thing that I want to test, okay? And both of these kinds of ideas are invoked to avoid including rotation in a calculation. Why would you want to do that? I mean, there's a long history in physics of getting rid of the degrees of freedom you don't want just because they're hard to do, right? To reducing it to something simple enough to solve, even if that simplification may or may not be right. That has a strong tradition. So the question is, in this case, is it a reasonable approximation? Okay? And again, the reason that they do that is to reduce that 6-dimensional problem to something that's manageable. Because you get rid of rotation, that's 2 degrees of freedom. Okay? And if you freeze the electron, you can actually get it down to a 1-dimensional problem. Okay? I'll show you that in a minute. Just to give you a sense of how these things compare. So if we go back to H2+, and that will be the focus of most of this talk, so I may not say it later. So H2+ dissociation, strong field. Take H2+, put a lot of photons in, you get dissociation of proton and hydrogen, and it's the distribution of proton and hydrogen that can be measured, okay? The relative momentum distribution. And that's what I show, say, in this column, and this column labeled experiment, okay? You can see the x-axis is, KER, that's kinetic energy release. That's the relative energy of the 2 nuclei, okay, of the 2 heavy particles, the proton and the hydrogen. This axis, cosine theta, well, theta is the angle between the laser polarization and the molecular axis, okay? And so you see the distribution, you see vibrational resolution here. Is it easier to see on those? Those tend to be a little bit brighter. But But you can see these vertical lines, okay? So those vertical lines are dissociation from a particular vibrational state. That one's probably B equals 9, B equals 8, B equals 7, okay? And that you can just tell by energy conservation, okay? It's not as easy to see there as it is in a projection down on just the energy axis, okay? This is an 135 femtosecond laser pulse. This is the same kind of distribution, but in a 45 femtosecond laser pulse, okay? All of these will be 800 nanometer, and yeah, intensities around 10 to the 13, 10 to the 14. That's not, in fact, quite so critical for this point. If you do the theory such that you take your molecule and just fix it in space at some angle, well, let me do it. I'll keep this the laser polarization. Okay, here's my molecular axis. If I fix this at some angle, solve the time-dependent Schrodinger equation, calculate the energy distribution of the fragments, okay, and then do that for all different angles, then I'm neglecting rotation entirely. I'm saying, so that's geometric alignment. It's also axial recoil, okay, because you're assuming that the fragments just go along that one line. If you make both of those assumptions, if you make both of those approximations, then this is what you get from theory for the same pulses. Okay? Now, these actually have one more thing done. They were actually averaged over the intensity distribution within the laser focus, because you have to do that to compare theory with experiment. But even so, I would be hard pressed to say that looks like that. Okay? And maybe even harder pressed to say that looks like that. And we were careful when we plotted these. All of these cover the same dynamic range. Okay? The density contours, they cover the same dynamic range. So it's not a plotting artifact as best we can make it. Okay? So these really look different, I would say. Now, if you include all of the rotation, then we have theory on this side, experiment on this side. Now these are all for 10 femtosecond pulses at different intensities. So the top row is 10 to the 12, the bottom one is 10 to the 13. Okay? And I would say, and those have been intensity averaged as well in the theory. And I would say those agree much better. Okay? So it would seem that rotation is actually fairly important to include to get the right answer, even when the pulse is so short that geometric alignment and those things seem like they should work well. Okay? So let's go, I want to go into that in a little bit more detail, try to understand that a little bit more to see just why that might be so.
Brett,
Yeah.
will you come back to something about rotation temperature and stuff like that, or?
Okay. So, no.
Okay.
But I'll answer the question. So one thing, and I glossed over this, I'm sorry, there's not enough time here to really give you all the details. You know, if I did that, we would get through all the details and have no time to talk about results. But one thing that you have to do when you do a calculation like this is you have to include the initial vibrational state distribution and the initial rotational state distribution in principle. Okay? Those distributions might be governed by some temperature or effective temperature. In H2 plus, it would be more of an effective temperature because H2 plus is created in an ion source from a gas of H2 by electron impact. So there's no thermalization, so there's no real temperature. Okay? So the vibrational state distribution here, and there's 20 vibrational states in H2 plus, is Frank-Condon basically. Okay? Frank-Condon distribution, if you aren't familiar with it, is just a vertical transition. Not sure that helps, but it peaks at about B equals 3 of H2 plus. Okay? The rotational distribution is reasonably close to thermal if you assume that those electronic collisions don't change the angular momentum too much. However, when you do the thermal average, you have to sum over all the m's for a particular J. Okay? Turns out that when you sum over all of those, the distribution looks awfully close to just J equals 0 because it adds up to essentially an isotropic distribution. So they aren't actually all that different than these. These only include J equals 0. These did not have the thermal average over rotational states included. They do have the average over the vibrational states included, and the intensity average. Okay? Again, for the students, ask about any of those things you want. I'm happy to explain it, I just didn't do it here. Now, you had a question?
You can explain why the theory is different from the current?
I hope so. If I don't, ask me again in a few minutes. Okay? I show those just to motivate that it looks like rotation is important. And notice, all of these pulses are shorter than the rotational period for H2+, which is about 300 femtoseconds. The free rotation period for H2+ is about 300 femtoseconds, and the longest pulse here is 135. Okay? First, I thought I would tell you how I include rotation. Okay? So we start, this is essentially talking about the Born-Oppenheimer approximation, but we start by writing down our time to finish Schrödinger equation. This is what we want to solve. The Hamiltonian is the Hamiltonian for the whole system. 2 protons plus the electron. So this is the kinetic energy for the relative motion of the 2 nuclei. This is the electronic Hamiltonian. This will be the interaction of the system with the laser field. The electronic Hamiltonian looks like so: kinetic energy, attraction to the nuclei, and the nuclear repulsion. Okay? And the interaction with the field is just the dipole interaction. Okay? So we're using dipole approximation, the length gauge, all of those kinds of things. The dipole operator looks like that in general for an H2 plus, for a H2 plus isotopal log. Okay? So if you have charges Za and Zb with nuclear masses Ma and Mb, then this is the formula. Okay? Normally, when you see this written down for H2 plus, well, first of all, H2 plus is homonuclear. So Ma equals Mb and Za equals Zb, so there's no nuclear component to the dipole. Okay? That's why people say homonuclear molecules have no permanent dipole. The permanent dipole people refer to as just this R-dependent contribution. Okay? Yeah?
Why do you put the nuclear interaction in the electron?
Oh, that one? Well, because it's, I'll show you in a second. Give me one more second. Okay? It's easier to explain once you see the picture. Okay? And then, of course, the R-dependent, or the electronic coordinate-dependent piece. And normally you see this with the masses of the nuclei taken to infinity. Okay? In which case this whole coefficient is written as 1. That's what Lars wrote down. That's what most everybody writes down. Because what's the difference here? Well, in any case, for H2 plus, this ZAB is ZA plus ZB. So that's 2 in atomic units. So it's, you know, M plus 2 over M plus 1. The difference is 1 in 2,000. Okay? That's why people don't normally write this coefficient. But I want to write it out in all its gory detail. Anyway, dipole operator goes in there. The Born-Oppenheimer part comes in because you say these nuclei are slow, right? They're much more massive, they're slow. So you fix R, the internuclear distance, solve the field-free electronic equation, okay? And when you do that, you get electronic states and you get electronic potential. The eigenvalues here are the eigenvalues of the electronic states at every internuclear distance. Okay? What that means is that you get a complete set of states at every internuclear distance. Okay? And of course, once you have a complete set of states, you can expand your wave function, or at least those degrees of freedom in your wave function, on that complete set. And so that's what we do. Okay? Put this guy back in our Schrödinger equation, and you get this equation for these chi's. Okay? The chi's in here, notice they depend on the internuclear position, the relative vector, and time. Okay? In the language that people use in Born-Oppenheimer, these are the electronic states, these are the nuclear wave functions. Okay? And you can understand why, because they depend on the nuclear coordinates. By the way, if it's a polyatomic molecule or a multi-electron diatomic, none of this really changes too dramatically. Okay? Instead of one R vector, there might be multiple ones for polyatomics, and for a many electron system, this guy simply represents a many electron wave function. Okay? Now, once you substitute it in there, of eigenvalue goes in there and acts as the potential energy for the nuclei. But then you have this term, okay? And notice what that does. That says that chi lambda, and lambda is one of these electronic states, gets coupled to all the other chi lambdas by these coupling terms, okay? This one, I'll tell you first, this one is Coriolis. We normally neglect that, okay? And you get Coriolis in there because when you solve the electronic problem, you do it in the body frame. And that's a non-inertial frame, so when it's rotating, you get a Coriolis term. We normally neglect that one. These two are non-Born-Oppenheimer terms. They're defined down here, okay? They're related to the radial derivative of those electronic functions because notice they depend parametrically on the internuclear distance. That basically represents some inertia that the electrons have. So when the nuclei are actually moving, they've got to drag those electrons along, okay? This looks kind of like a nuclear momentum. DDR looks like a nuclear momentum. So this is something like an extra bit that when the nuclei move, they have to drag the electron, okay? But what that does is it couples state lambda to state nu, okay? The final one down there is the dipole interaction, and you can see it also couples different electronic states, okay? Which of course is good because when you shine a laser on there, you want something to happen, okay? So, I just want to mention a couple of things about these non-Born-Oppenheimer terms because there's something that's actually being studied quite a lot these days in strong field physics, okay? In this problem, not in H2+, but generically in, say, an diatomic, you might have potentials that depend on the internuclear distance. Maybe you have something like this, okay? And this spot is a special spot. That's called an avoided crossing, okay? Now, what we know is that this P and this Q, they peak right at that crossing. So when these energies come together, the likelihood that you make a transition via this coupling gets much bigger, okay? That's one of the advantages of having these adiabatic potentials is that where you see these avoided crossings, you have a chance for a transition. So you can go from this electronic channel to that electronic channel, okay? This kind of a picture really sort of evolved in the collision community. But I think you can appreciate why potential energy pictures are favored, are useful. And after all, from your first physics class, you were taught to look at potential energy and kinetic energy. Even when you took your advanced class, you talked about effective potentials because those are useful ways to think about things. So these are effective potentials for this nuclear motion, okay? Notice, if those aren't there, and we have no field, then this is a problem that separates, okay? So you're essentially you're trying to separate these degrees of freedom, the nuclear and the electronic, okay? And that's not exact, so there has to be some coupling between them, okay? And that's what this reflects. These transitions that might happen at such an avoided crossing are called radiationless transitions sometimes, okay? They're driven by non-Born-Oppenheimer coupling. In polyatomics, and that's where the field is really interested in these kinds of things. In polyatomics, the potentials don't depend on just one internuclear distance, they depend on several. That means you have potential energy surfaces, and where those guys come together is called a conical intersection, okay? And that's where polyatomic species can make transitions without emitting any radiation or absorbing any radiation from one electronic state to another, okay? That's the importance in a broader sense, okay? So all we've done is go to a basis of these electronic states and write down our Schrödinger equation. So that's what needs to be solved computationally, okay? These guys, remember, depend on the full internuclear vector. So all the angular degrees of freedom are in there. Rotational kinetic energy is in there. So we just solve this numerically. We expand the nuclear wave function on partial waves, That gives us coupled 1D equations and the internuclear distance. Okay? For H2 plus, we can get rid of all of these guys. And the transitions are just governed by this dipole operator. Okay? Okay? Like I said, I'm not going to tell you the computational details, but I'm happy to answer anybody's question on that later. This is what the potentials look like for H2 plus. Okay? Now, we have internuclear distance and we have potential energy. So this is energy, this is in atomic units. The bound vibrational states have to live in this well, below the lowest threshold. That's where your bound states will be. Asymptotically, it's going to go to a proton plus hydrogen. Okay? But of course, this state is the 1s sigma g, so I've labeled all the sigma g states are black. The sigma u states are red, and the sigma is the angular minimum around the molecular axis of the electron. G and u are, think of them like parity. They determine selection rules when you absorb photons. Okay? But I've also shown here the n=2 manifold of curves for H2 plus. I've also indicated up here at 0 the ionization threshold. So this is the asymptotic ionization threshold. Okay? But what that means is that, okay, so these go to proton plus hydrogen in the 1s. These go to proton plus hydrogen in some n=2 state. Well, between hydrogen and n=2 and hydrogen, well, ionized, there's a whole infinity of states in there. So I've left out an infinity of states in this picture, right? Manifolds like this that converge to P plus H n=3, n=4, n=5, the whole Rydberg series. Okay? Yeah?
One question to your sketch there.
Yeah?
So, the matrix element has this derivative with respect to the nuclear coordinate.
Right.
So one can think about this like about the momentum.
Right.
So can one think about this whole process there like in terms of Landau-Zener tunneling? That the
Oh,
faster the
this is
molecular motion, the
absolutely. I mean, you can, yes. This kind of a crossing, Landau-Zener is the model for that kind of crossing. Landau-Zener was basically generated in the first, they came up with it in the first place to describe these kinds of things, because it was really collision problems. Okay? Okay, so these are potential curves, and for the most part, the nuclear interaction was included so that all of this potential represents all the interaction between the nuclei. Okay? Because the if we go back, this potential energy here, that's the potential energy, that's the interaction between the nuclei. Okay? And if we left out the 1/r between them, it would have to be added there and you would sum them up to get the whole thing anyway. Okay? What else? Well, dissociation, of course, is you start in a vibrational state here, you absorb a photon, and you get above this energy. Okay? And for the most part, in strong fields, what people include are only these two states. They leave those out entirely. Okay? And the reason is that between here and there is about 10 eV. At 800 nanometers, 10 eV is how many photons? 6, 7, something like that, right? So you need 6 or 7 photons to get up there. Okay? The intensity needs to be rather high for 6 or 7 photons to come into play and take you up to those states. Okay? In practice, around mid 10 to the 13 watts per square centimeter is enough intensity to start bringing these into play. Okay? These are what the dipoles look like. Remember, in our equation, what was driving transitions is this dipole matrix right there, right? This is what they look like. Normally, people only talk about that guy, which keeps going up like r/2. Okay? It's really simple. It just diverges, r/2. The rest of them, though, do come in if you have to worry about going into n = 2 manifold. Okay? Again, for the most part, that's what dominates. If you actually do calculations now, we can calculate, say, from different initial vibrational states, we can calculate the total dissociation probability. Okay? What I'm showing here is exactly the total dissociation probability as a function of intensity. Notice the scale is different in these different plots for 3 different pulse lengths. Okay? And again, what we want to test is what is the role of rotation? Well, in each of these plots, I'm showing 3 different approximations. Okay? The one that you should consider exact, the one that includes rotation, is the blue one. Okay? The blue one is circles in here. That's the exact one. If you just fix the molecular axis to be exactly along with laser polarization and don't let it rotate, which is what most people do when they do calculations on H2+. Okay? That's this magenta one. That's the triangles up here. Okay? And if you make a little more sophisticated version of that model, in other words, you take the axis to be fixed, but not just along the polarization, but every angle, and then average over all of those to represent the initial isotropic distribution, that is the red one. Okay? It's the average of the no rotation. I'll explain that just after I answer the question. Yeah?
The V equals 7, 9, and 12, what does that mean?
That's the initial vibrational state. Okay?
So what are the numbers, like 7, what is?
So vibrational states start at V equals 0. That would be the ground state.
Okay.
Okay? And for H2 plus, it goes up to V equals 19. Okay? That's the last bound state in H2 plus for J equals 0. So yeah, V equals 0, 1, 2, 3, up to 19. And so I just picked a few of these out. Okay? We picked 9 because it turns out that's the one that dissociates the most, typically in 800 nanometer light. Okay? And these are just representative other states. Okay? You'll notice in almost every case that the calculation with the molecular axis just along the polarization overestimates dissociation probability. Okay? Which makes sense in a way because you've taken the one that sees the maximum field. Okay? Along the laser polarization, that's the maximum field. Okay? So that always overestimates the dissociation probability. And this is, in fact, characteristic of reducing the dimension of a calculation. Okay? Anytime you cut out degrees of freedom and don't represent them in any way, anytime you cut those out, I won't say anytime, most every time you cut them out, you overestimate ionization, dissociation, and all of those things. Okay? Moreover, you'll notice that these reduced dimension ones, the ones with no rotation, the dissociation probability goes up and then back down. Right? Reminiscent of the stabilization that Lars was talking about, that other people talked about long ago. In the molecular problem, that's called vibrational trapping. Okay? We'll get to that in a second. So the calculation with the fixed axis shows vibrational trapping, shows this stabilization-like behavior in many of these cases. But the exact calculation shows it basically in no case. In no case does the dissociation probability go back down in this range of intensities. However, one interesting thing is that if you take your molecular axis and average it over all those angles, it doesn't do too bad in many cases. Okay? It doesn't do too bad in many cases. The cases that it does best are the short laser pulses. Okay? And again, given our argument earlier, that probably should make sense to you because the laser pulse is so short it has no time to rotate during the pulse. And in this calculation, we're just asking about the total dissociation probability. So we don't care about any rotation later. All we care about is what happened during the pulse. Does it dissociate or doesn't it? However, if you look at 135 femtoseconds, that kind of average one doesn't agree with the exact one. Okay? Which should suggest to you that maybe in 135 femtoseconds, this molecule really is rotating. Even though that's much shorter than the free rotation period, it really has time to rotate. And so simply averaging over a fixed molecular axis is not enough to give you a good answer. Okay? Yeah?
Can you comment then if that's why the pink is good? Because that would seem to be worse if it's rotating than the averaging over it.
Why is the peak, oh, why is
Pink
the,
one, why is it close to blue? If,
why is it close to the blue? Because in 135 femtoseconds, what happens is the molecule essentially lines up perfectly with the laser polarization during the pulse, which is exactly the model that the magenta line is showing. Okay? And if you calculate the alignment, right, the degree to which the molecules lie along the polarization, as a function of time, you can see that. I didn't put that plot in here, but that's what you see. Because you can actually see that in this case, the molecules align during the pulse. Okay? So I would say that these plots suggest, even for these short pulses, that you probably ought to include rotation, or at least the rotational average, to avoid errors like vibrational trapping. I put errors in quote, but because it's something that you get misled into believing if you look at these reduced dimension calculations. Okay. Now, vibrational trapping, does anybody know what vibrational trapping is, or why people even expected it? Okay, well, let me take one more trip to the whiteboard, and I'll answer Laura's question from the other day about talking about Fouquet. Okay, because when Phil was doing measurements on H2+ back in the early days, they saw a lot of these phenomena that I'm talking about, and they explained it with this picture called Fouquet. Okay? And it's based on taking these worn-off nitro potentials. Of course, in H2+, they look like this. Okay? Fouquet, can everybody see this color? The marker doesn't look so good. Fouquet is a way to take advantage of the periodicity of the laser field to do some mathematical manipulations. I'm not going to explain the math. I'll just tell you the recipe for what you do. Okay? You dress the potential curves by some number of photons. So you would take this 1s sigma state, say with some vibrational state in here, we'll call that 0 photons. Okay? Now, when you absorb one photon, you have to go to the 2p sigma u state. So this is 1s sigma g. This is 2p sigma u. Okay? And I wrote that in an unfortunate spot. Okay? So this one is 1s sigma g. Fouquet says you dress this, so you move this one down by 1 photon. So that would be n equals 1, and that spacing is exactly omega when h bar is 1. Okay? Now, you dress the 1s sigma g down by 2 photons, so that spacing is omega. And you do the same, you dress 2p sigma u down by 3, n equals 3, so there's omega. And you keep doing that. You just keep shifting these down, making more and more copies of this. Okay? We know that the 0 photon and the 1 photon curves are coupled by the dipole matrix elements. Okay? So that means that there's coupling right there. Okay? There's coupling right here. Now, the 0 and 3 photon curves aren't directly coupled by a dipole matrix element, but they're coupled by a 3 photon transition, so there's an effective kind of coupling here. And the idea, and we can write it out, maybe I'll do that in my last lecture. You can write out a matrix with all these dipole couplings, you diagonalize that matrix, and what that gives you are worn Oppenheimer potentials with the effect of the field included. Okay? What that does is it makes an avoided crossing here, just like I sketched before. You have a non-adiabatic transition possible here. Okay? You also get an avoided crossing there and an avoided crossing there. Okay? So those are your new potentials. When the field is on, these are your new potentials. So this vibrational state would tunnel through the barrier here and dissociate, and that would be its kinetic energy. Okay? By the way, molecules don't really tunnel. Nuclei don't tunnel. Okay? They're too heavy. They can't tunnel very far. So the lowest one that really gets out is the one that's right at the top of the barrier. So it will come out and have that much kinetic energy. However, we started with vibrational states all the way up here. So some of these actually get caught in this well that forms out there. Okay? Those are said to be vibrationally trapped. Okay? Because if they're trapped in the well, they can't really get out here very easily. So it's expected that those states won't dissociate as much. The dissociation probably will go down. So that's this picture. V equals 12. V equals 9 is right here, right in the middle. That's why we showed V equals 9. It's right in the middle. So when the field turns on, it comes out immediately. Okay? V equals 12 is up here. And you can see it shows all this crazy stuff. By the way, in this picture, there is no angle. This picture is drawn assuming the molecular axis lines up perfectly with the laser polarization. Okay? And so, in a sense, we've done the same reduced dimensionality trick that we did to get this magenta curve. Okay? And so people expected vibrational trapping. Yeah?
How does your picture depend on the intensity? So you get this oscillation?
This gap at a fairly simple level is related to basically it's 2 times the field. Okay? So as the field grows, that grows. It's not quite so simple as that, but qualitatively, yes. As the field grows, that gap gets bigger. I'll show you a picture in a minute. Just exactly how it looks. Okay? So people expected vibrational trapping, and they saw it in their calculations. Everybody was happy. Okay? Except that when you actually include rotation, it seems to go away. And people found that out long before we did these calculations. We weren't the first ones to say that.
Why is that?
Why is what?
Why do you move to that?
Oh, well, one answer is when you include rotation, there's another way for it to go. So the ones that get trapped here, they can sneak out another way and dissociate. Because they can turn and get away. Okay? And that's generally what happens when you go from the reduced dimensionality to higher dimensionality. Is that you can see these other possibilities for happening changes things dramatically. Another reason that folks expected vibrational trapping or talked about vibrational trapping is because when they plotted dissociation probability, say the total dissociation probability, as a function of V, when they did this calculation without rotation, they saw, for instance, this big dip right here. Okay? So dissociation probably goes up, it's almost 1 for these intensities. But as you get up to V equals 12, which again sits up here, which you expect to be vibrationally trapped, you see this big notch, you see this big dip. It doesn't dissociate. Great, vibrational trapping, that works. Okay? And you can see that as you go from 10 to the 11, which is this one, to 10 to the 12, that one, you can see such behavior. You can see these states, in fact, the higher intensity has a lower probability. Okay? This is the calculation we did with rotation. And you can see the increase is just simply monotonic. But you do still have a dip there. So how do you understand that dip? Is it really vibrational trapping? Maybe it's still there. Well, if we do the calculation in first order perturbation theory, okay, because all of these states can dissociate with 1 photon. If we just calculate the dissociation problem in first order perturbation theory, we get the red curve. Okay? So the reason there's a notch there, the dipole's small. There's simply no dipole to dissociate from V equals 12. It has nothing to do with multi-photon effects, it has nothing to do with vibrational trapping, which is a multi-photon effect by definition. Okay? It simply exists, or doesn't exist, as dissociation, because there's no dipole. So this is one important thing to remember. Even though you're doing strong field things, especially when you're doing it with nuclei, don't forget to look at what first order perturbation theory gives you. Okay? Because at the very least, when you see deviations from first order, you know that's multi-photon for sure. Okay? So, we're getting a little bit late, so what do I want to show here? We can look at angular distributions. So if you want to talk about the other approximation, we talk about geometric alignment. So if you have laser polarization, and you have this isotropic distribution of molecules, geometric alignment, remember, is that those molecules in this direction will dissociate. If that's true, then if you look at the bound part, you should see holes start to develop in the bound part, right? The distribution should get pinched. Well, if we look at v equals 6, v equals 9, and v equals 16, in this kind of a laser pulse, 5 femtosecond, 800 nanometer, let's see, T1, that's just this, let's see, black dashed line. That should be isotropic. I don't know if the aspect ratio looks like it, but the black dashed line is isotropic. At T2, right, you should start having some dissociation. That's this one. It's actually, okay, it's a little flatter, so maybe you're, oh wait. Oh, that's no good, because the polarization's this way in the pictures. So you actually don't have a hole there. It's going the other way. Well, okay, that's not quite what we expected. This blue dashed line, oh, it's not much different. And at T4 at the end, you see it's actually aligned with the field. But really, there was no place where holes got burned in there, okay? Which I would say is evidence that there's not much geometric alignment in v equals 6. Now, in v equals 9, you can see that there is a deficit along there for the red one at T2. So a little bit of the things along that direction did get dissociated, but it quickly recovered to fill that out, okay? And again, you can go through these pictures, and because of time, I won't go through all of the details, but there's no drastic evidence, there's no sort of dramatic evidence of hole burning in these, which would seem to indicate that there's not much evidence for the geometric alignment here. It's true that when you measure the final distributions, it tends to be aligned along the polarization. But that doesn't mean that you preferentially dissociated the things that were started along the polarization. That just means they ended there. Okay? I'll just explain what this is about. So one argument would be that, okay, H2 plus is the lightest molecule, which means it rotates the fastest. So if there's going to be a geometric alignment, if there's going to be hole burning, maybe it's not going to be on the one that rotates the fastest, but maybe on something that rotates more slowly. So we just simply increase the mass from H2 plus to T2 plus, and then to a fake O2 plus. We kept the same potentials, we just increased the mass artificially. Theorists can do that, okay? You don't see any real dramatic differences, okay? There's still no strong evidence of this hole burning or geometric alignment. That raises the question about axial recoil. Axial recoil, remember, is, okay, we're done with the pulse. Do the fragments just go in a straight line to the detector? Or do they maybe curve and rotate on their way to the detector? Okay? And so one way you can look at that, and again, we can only do this in theory, is we can calculate the angular distribution at the end of the pulse, T final, that's the red ones, and the angular distribution at T equals infinity, that's what you would measure in your experiment. And you can see that this is, okay, 10 femtosecond pulse, 5 times 10 to the 13 watts per square centimeter, 10 to the 14, and a 5 femtosecond pulse. And you can see that the angular distribution actually changes rather dramatically from the end of the pulse to T equals infinity. Okay? If you quantify that by calculating the alignment, which is calculating the width of this distribution, that's just expectation value of cosine squared theta, then you can see down here as a function of intensity, the relative change, which is the, I don't know, pinkish purplish circle one, the relative change in cosine squared theta from the end of the pulse to infinity gets up to about 10%. Maybe, I don't know, well yeah, over here. Gets actually above 10%. But folks that are doing alignment, that are purposely trying to align molecules, have worked really hard to get a 10% relative change. That's actually a very big change in the alignment. Okay? And that's what you can see in these kinds of plots, that the change is actually fairly dramatic. Won't go through that one, but I do want to show this one, because this actually gets at the same kind of question. Okay, hydrogen is a light molecule, maybe it's just rotating faster because it's so light. Well, what if we artificially, the dash is at the end of the pulse, and the solid, the blue line, is at the detector. And okay, so these kind of have the same shape, but clearly the width is different. The cosine squared theta changes by 14%. These actually look pretty good, right? Those match pretty well in that case, but this one is fairly dramatically different. And these are from different, let's see, what are these? These are a specific initial vibrational state and different wavelengths, okay? This one also, fairly dramatic difference. Okay. So the point is, that just because you might measure this final distribution, say the blue one, it may not be safe to assume that that was the distribution when the thing broke, okay? Because this dashed line is the closest we can come to that distribution when it broke. So axial recoil looks like it might have, there should be some caveats. Now, a thing to keep in mind, the dissociation energy of these things is on the order of an EV, okay? And you might be creating, I mean, in this case, you can see there's lots of angular momentum in that wave function. That's how you get so many lobes. So that means that the radial kinetic energy isn't so large compared to the rotational kinetic energy, okay? Which was the underlying assumption of axial recoil. So it's not necessarily a surprise here. So the things that Paul was talking about, Coulomb explosion imaging, where you go up onto this repulsive Coulomb potential, you have this whopping big radial kinetic energy compared to the rotational energy. Axial recoil probably doesn't work too bad there because it will fly apart before it can rotate, okay? The caution here is just remember that when you're doing strong field and you're doing dissociation, that may not be true, okay? And it may be dramatically not true. It's getting late, I won't talk about this one. The key point is that including rotation is actually fairly important if you want to make quantitative predictions compared with the experiment, okay? Because experiment measures angular distributions. So you need to include the angular degrees of freedom to produce predictions. We talked about these things. One thing is that we check things only for H2 plus potentials, okay? It will be interesting at some level to check what other kind of characteristic shapes of potentials will do. But again, I expect this is the ratio of radial kinetic energy to the rotational kinetic energy that will matter, okay? And I guess I will stop there. Thank you.
Thank you so much. We have time for questions, comments. Yeah.
So, seeing the difference in the axial recoil and the exact,
Yeah.
there's no real way to do the experiments better in that case, is there? Or
No, that's-
so. What's the? Is it just a caveat when you're doing the interpretation, or is there a way to?
Yeah, I would say it's a caution to use the language more carefully,
Okay.
right? I mean, once you measure the momentum distribution in infinity, unless you can argue that, again, the radial kinetic energy is much larger than the rotational one, then all you can say, this is what it is at infinity, right? I just wouldn't say, that's what it was when it broke,
Yeah.
okay?
Yeah, sure.
So I would like to hear your point of view. If now you have an aligned example of molecule.
That.
Okay. We planned this.
No, we asked this question too, because in fact, there's a lot of interest in aligning molecules, and mostly people think about ionizing those things. So we said, okay, what happens when you dissociate them? Well, if you align it really well in some direction, then, and you dissociate it, if axial recoil is true, it should just go that direction, right? And that seems like a good case to check. And again, the side monitors might be better to see this. You can see, so theta naught is the angle between the alignment angle of the molecules and the laser polarization, okay? So this angle is theta naught. So the molecules are aligned with a degree of alignment of about 0.9, which is pretty good alignment, okay? Around this angle to the laser polarization. So if axial recoil is true, then the angle they dissociate to, which is plotted here, should just be equal to the initial angle. So in other words, this peak should fall along the line theta k equals theta naught. And you can see that for low angles near the polarization, that's more or less true. But you can especially see on the side monitors that as the alignment angle approaches really about pi over 4, that's no longer true. Okay? That's no longer true. That the peak of the distribution is really sort of along there. It just kind of goes straight across. Yeah?
Well, I think that answers this question about what can an experimentalist do, because this is what, in fact, one does, is invoke the one other piece of information that you have, which is energy conservation.
Right.
And if you discover that there is kinetic energy that's kind of missing, in other words, you can't account for the energy of the recoil just by looking at the angles that things appear, then it's because you put energy into rotational motion. So you see it directly there. If I'm understanding what the y-axis is.
Yeah, I mean the y-axis is the angle of the fragments at infinity. So integrated over everything else, energy and everything else.
How would this, so this was for dissociation, so if now we had breakup, it would be better, right? In the sense that you would have less effect of this exact treatment of the rotation.
Sorry, say that again. This is dissociation, right?
Yes, this is dissociation.
Yeah.
Now you had ion state.
Okay, so if you're going up to, say, a repulsive Coulomb curve and you have a lot more radiokinetic energy.
Then you would expect it to be accurate to use the...
Yeah, although in this case, I still don't expect it to go all the way down, because if it's perfect down there, there is no transition, right? That's one thing that we didn't really get into, is that H2 plus, if you only have 1s sigma g and 2p sigma u, it only has parallel transitions. And so if it were perfectly aligned, if it were no rotation included, and you align this thing perpendicular to the polarization, you should see nothing at all, because there is no transition dipole moment then. So the fact that you see something even over there, when it's aligned perpendicular, that contradicts that model. And of course, the interpretation, I think, is just simply that we don't have a perfect alignment, we have a distribution, so the wings of our angular distribution are getting dissociated even when the center is at pi over 2, even when the center is at 90 degrees. Yeah.
If you look at angle not at infinity, but at some finite distance, can you just infer the amount of rotational energy?
Sure, and that was a plot that I asked my student to make, is just take one of these guys and make the movie and see if you can watch it curve out to infinity. That would be fun. But I don't think he's made that one yet. Yeah.
Born up an angular potential on your show, it seems that by one photon you can dissociate the molecule.
Right.
But you have another open angular potential after that. It seems that by multi-photon you can go over there and still you are in the binding, not dissociated.
Oh, you're talking, okay.
It seems a little bit counterintuitive. By one
Let's see.
photon you dissociate, but by multi-photon you still in the...
So you're talking about getting trapped up there, for instance. Okay. So it sounds strange to you that you can dissociate with one photon, but you can put more energy in and not dissociate. Yeah, I mean, you say it that way, it probably does sound kind of counterintuitive. But I think when you look at this, it's not too surprising, right? Because if you go from one well to another, which is not very likely here, by the way.
Right.
Because, again, if you think Frank Condon, you're going to go straight up, and that puts it up here on that curve, and that's definitely going to dissociate. And I can tell you from the calculations, we don't get very much that sticks in there. Because we've included these in the calculations. And what you see is really high energy dissociation on those channels. But you might be able to find a molecule where that can happen. Yeah. Well, you're just pumping the energy into the internal excitation, right?
Well, if you start, I guess, from just below the ionization level, you might get there, right?
Oh, you mean if you start out here in this high vibrational state?
Yeah.
Yeah, you probably have some chance.
Yeah.
The problem is that state is like 0.002% in the initial distribution.
Right.
Yeah. So there just isn't much of it to contribute. If you could prepare it that way,
Right.
but that's something folks aren't able to do so well these days.
You have to control power.
Exactly. Yeah.
Are there further questions or comments? If not, thanks again so much.